నాగేశ్వరరావు కొంచెం అందరినీ జాయిన్ అవ్వమని చెప్పరా? నాగేశ్వరరావు మీరు లైన్ లో ఉన్నారా?
ఎస్ మేడం.
కొంచెం అందరినీ జాయిన్ అవ్వమని చెప్పరా? ఎక్కడున్నారో తెలియదు వాళ్ళు నాకు.
ఓకే మేడం, ఓకే నేను చెప్తాను మేడం, గ్రూప్ లో
జాయిన్ అయ్యారా?
మేడం జాయిన్ అయ్యారు మేడం.
సరే, ఇంకా 3 minutes ఉంది. 3 minutes వెయిట్ చేద్దామా?
మేడం
సరే సరే. స్టార్ట్ చేద్దామండి. నాగేశ్వరరావు స్టార్ట్ చేద్దామా?
ఎస్ మేడం.
ఓకే, I'll put it in recording mode. మణి గారు స్టార్ట్ ఉన్నారండి మీరు?
ఉన్నాను మేడం.
సరేనండి. Participants, I will introduce Mani madam now. Dr. V.V. Mani received her BE ME degrees in Electronics and Communication Engineering from College of Engineering, Andhra University, and PhD in Electrical Engineering from IIT Delhi. She joined NIT Warangal in April 2008 as Assistant Professor in EC Department, where she has been a professor since March 2022. She headed the Computer Center NIT Warangal as additional duty in the year 2019-21 and also served as an Associate Dean Staff Training and Recruitment for the year June 2023 to June 2025. Prior to joining NIT Warangal, she worked as a software engineer, Capricorn Global Solutions Private Limited, Hyderabad. Also worked as an assistant professor at Geetam University and full-time research associate at IIT Delhi. Her area of interest includes wireless communication, signal processing for communication, optical communication, and design of real-time test beds for 5G using SDR. She has more than 100 papers to her credit in both national and international conferences and journals as well. She supervised 10 PhD students, and currently 5 more students are working under her towards their dissertations. She completed 6 projects and 2 more are ongoing with the DST SERB, UKIERI, Spark, India Asian with international collaborations. She visited many countries and presented her research papers. She spent 3 months at Rice University, Texas, USA, under Research Exchange program. She held various administrative responsibilities at NIT Warangal and also served as a student branch counselor for IEEE student branch at NIT Warangal and won Darrell Cheng Bronze Award for best student activities. Dr. Mani and her research team developed a wireless communication laboratory for MTech Advanced Communication Systems using SDR platform. She is a fellow of Institute of Electronics and Telecommunication Engineers, India, and senior member of IEEE. She published a book with CRC Press on Visible Light Communication, Comprehensive Theory and Applications with MATLAB. Yeah, that is the introduction for Mani Madam. Mani Madam, please proceed, Madam.
Thank you, madam. Thank you for the introduction. Is my voice audible, madam?
Yes, ma'am, it is audible.
Okay. Just give me a minute. Okay. So, dear participants, welcome back again to the today's session on Estimation Theory Foundation for UAV Communication. So, this my presentation is on teaching board. So, mostly I write equations. So, wherever it is necessary, I write the equations. Otherwise, I speak for some content. I hope you can understand the procedure of making a note of everything what I am saying in this today's session. So these USB communication systems, we need a reliable data transmission, localization, navigation, target tracking. It depends on accurate estimation of some unknown parameters, right? Such as channel state. What is the channel state of your communication, UAV communication? What is the position of your object, velocity, and what is the orientation? So for everything, we need estimation. Like I'm listing out channel state. I'm listing out the channel state information, velocity, and orientation. Right. So for these unknown parameters, we have to do some estimation. So this estimation is actually a mathematical framework. Estimation theory is nothing but a mathematical framework. It is a math framework. So this infer these parameters from noisy environment. So why it is more important? Suppose, so I am taking one example in the estimation theory. So this estimation theory is actually deals with extracting the useful information. So parameters of the state which I mentioned earlier, like these parameters. Now let us take one example, y equal to suppose h of x plus n, right? So y is your observed data. You are observing the data. and h of x, whereas hidden parameter x, right, to be estimated. So the parameter or state to be estimated is your h of x. That is your channel coefficient or UAV position is to be estimated. And anyway, we know very well this is additive white Gaussian noise, AWGN noise. So this H corresponding to your system model. So you are having some system model and you are sending this the model of your information. When you are transmitting this information, it is added by additive white Gaussian noise N. So then how to find that estimate of x? So we are sending some information x. Then so when it is added by additive white Gaussian noise, we need to estimate that parameter. So this parameter is approximately or closely must be equal to your original data of transmission, original information, possible to the true value, maximum value. Okay. So in such cases, we can talk about some types of estimations. Is it a parametric, that means a parameter estimation, or a random process estimation? I am just writing the types of estimations. So what you have to estimate in your UAV communication. So your types of estimation. So they can be deterministic, non-deterministic, two cases, right? So deterministic, that means deterministic parameter estimation, and say there is deterministic parameter estimation and stochastic. Is a deterministic. If it is a non-deterministic, we call it as stochastic. So stochastic estimation. So that comes from random process RP. So random process estimation, and so that means in deterministic parameter estimation, estimate some fixed amount, but it is an unknown parameter. So like one example I can give. Suppose A is one value you are transmitting. This A is when you are transmitting a pulse for a duration of T with an amplitude of 10 volts, right? So that is what is the parameter you want to estimate? A you want to estimate. Then what is the amount of that A? The value of A is 10. So that means it is a fixed. But it is unknown to me because when you are transmitting, when you are sending this information through your UAV communication, so A is added by additive white Gaussian noise. It is a fixed quantity, but it is unknown to the receiver. So unknown to the receiver. Then it has to estimate the value of A estimate has to be approximately equal to A. So one such examples in communication system or in UAV communication, or one such examples of it is a fixed amount, but it is an unknown parameter, like your channel gain is an unknown parameter. So channel gain is an unknown parameter, and path loss exponent is also an unknown parameter, right? And Doppler shift in UAV communication is also an unknown parameter. So these parameters are to be estimated. So this is one parameter estimation based on deterministic nature for the UAV applications. If it is stochastic nature, then the second case is for the stochastic nature. So there is a time varying random states are happening. So the examples are, because with respect to time, the value of the estimate, the value what you want to estimate is also changing. With respect to the time. What is it with respect to time? That value is going to change in UAV communications. That means your UAV position is one of the parameter. So this position with respect to time, so your UAV object is moving from one position to the other position. So at t equal to 0, this is placed at initial position, but at t equal to t naught, t equal to some t naught is placed at another new distance, right? So that means the position is stochastic in nature. We don't know how to, this is becoming a random variable now, because initially is at one position, now it is changed to a new position. We have to predict that new position. And also target tracking is another parameter. So we have to estimate. We want to track this object continuously as it is moving from one position to the another position, right? So this is one kind of type of an estimation. Another estimation is Bayesian estimation. So this Bayesian estimation takes some prior information of the values, like we are estimating a position of an EAV. So, or velocity of a EAV, or we are tracking the EAV. So, in such cases, what is the initial position of EAV is known. Some prior information is known to me, or what is the probability of your UAV placed at a certain position? Is the probability of your UAV placed at a some distance x. So this is known prior information. So then we can use the Bayesian estimation, right? So this Bayesian estimation uses the prior information probabilities, like your sensor fusion using GPS is one of the example where we use the Bayesian estimation. Then another kind of estimation estimators are adaptive estimation. So this adaptive estimation updates the parameters, like one position is estimated. At position, that means the distance from T naught at T equal to 0 to T naught, then the distance traveled by the object maybe will talk it as X, right? So that is our X. Now adaptively we are, when the target is moving along the axis, suppose it is reached to the next position, that means X plus some delta X, right? So that means we are updating the parameters, update parameters in real time. So we are estimating in parallel. So like one example is adaptive beamforming, real-time channel tracking are all the examples of your estimation foundations which are required for any kind of communication, any kind of object detection, any kind of object tracking. We need some of the parameters have to be estimated. So these estimation problems in EAV communication, we are making into generalization, making towards the particular to the EAV communication. The first one, as I said, it is a channel estimation, right? So first one, as I said, it is channel estimation. So in this channel estimation, actually, the channels are very rapidly changing. So the channels are very rapidly changing due to the mobility of your 3D propagation. So here in channel estimation, mostly we use least squares estimate. Least square estimate, we call it as LS. Least square estimate. Minimum mean square, minimum mean square error. This is called MMSE, minimum mean square error estimation. So that means, what is this minimum mean square error? Suppose I am estimating a parameter like your previous example, y equal to the known data we are sending, and it is added by additive by Gaussian noise n. Then we have to estimate the parameter a. So a estimate we have to estimate. So in this minimum mean square error estimation, we have to minimize the error between the original value and the estimated value. So this square value of this signal error must be minimized. So for that minimum value, for which value of a the error is very minimum, we have to estimate that parameter. Yes. So another estimation for EAV which is helpful in parameter estimation is Kalman filtering. Is very, very important. Kalman filtering. So this Kalman filtering for only time varying channels. We use Kalman filtering for time varying channels because EAV is also moving along the time changes. So we applied Kalman filtering for time varying channels, channel estimation. So in this Kalman filtering time varying channels, so what generally we do, we are estimating the channel. So the channel is argmin of the original value y is your signal, minus xh norm square over h. For which value of h? So which value of h? The received signal y and the transmitted signal x multiplied by h, that means y equal to xh plus n, right? The signal is convolved in the frequency domain. If you write, generally this the convolution between two signals x and h are convolved. The x of t is the transmitted signal, h of t is the channel information. These two are convolved. So I am writing it as y equal to xh plus n. Then we have to see that y minus xh norm square, so that it is equivalent to nothing but your norm of noise, right? So norm of the noise. The noise has to be, that means when you are minimizing over per particular h, this is also minimized. So this is like that we adopt your estimation procedures. Just I am going through the how we have to apply your estimation techniques, estimation foundations, which are helpful in UAV communication systems, like localization and navigation. So in estimation, of a UAV position, right? So we are estimating a UAV position. So what is the position? Any UAV is placed at X, Y, Z geometry, right? So using the GPS. So we do using the GPS. It is placed at this geometry. So now so this is one of the positions we have to estimate. Okay, like in tracking, target tracking. So multi UAV estimation, target or peer estimation positions. So distributed estimation and consensus filters are used for the estimation. We'll go deep into the one by one with an application of UAV. So now the spectrum sensing and the signal detection is also very important in UAV. So UAVs are actually acting as an aerial base stations. So estimation of the estimate the spectrum occupancy using maximum likelihood or Bayesian. So Amerit or Bayesian also we use. Okay. So first, the key mathematical tools which generally we use in estimation of a parameter is expectation operator. So that is expected value of x minus x estimate whole square, right? So this gives you the variance of the parameter what you are estimating. X is the original signal, x estimate its estimated value, right? So we adopt some estimation procedure. So after adopting the estimation procedure, we try to see that the value of this square signal, x minus x estimate whole square. This is nothing but, if we know very well, suppose x is a random variable with mean Gaussian distributed random variable with mean 0 and variance sigma square, right? So then what is the expected value of x if you see? What that means, the mean value is 0. What is the sigma square? Sigma square means variance. That is expected value of x minus its mu x whole square, right? Similarly, in the estimation also, we do x minus x expectation whole square. So this is a measure of the estimation accuracy. This is called measure of estimation accuracy. Measure of your estimation accuracy. Okay. Now also we have to use the Kramer-Rao lower bound, CRLB. This is actually, it is called CRLB, Kramer-Rao lower bound. So Kramer is a foreign inventor. Rao is an Indian author. They both together found a lower bound for the variance. This is actually a theoretical accuracy limit. So generally, theoretically, we can get this much of accuracy. So this Kramer-Rao lower bound calculates the variance of the estimated. Variance of the estimated. So we have to measure this one as the Fisher information matrix. In the coming pages, I'll explain what is a Fisher information matrix. So this is actually a theoretical accuracy limit. This Cramer-Rao lower bound tells us beyond this one, your bound, that means the accuracy will not go down. That is the meaning. So this is a theoretical accuracy limit. Okay. So like that, we will use some mathematical tools for the parameter estimation. Now, so we want to see the relevance to UAV communication systems. Suppose UAV is there, UAV function, and what is the estimation role? So UAV and estimation. So your UAV function, and how do you do the estimation? So channel state information, CSI, is one of the parameter, right? So estimation, what we adopt for this estimation, like your adaptive modulation, beam forming techniques, adaptive modulation, beam forming techniques we use. Then another function is navigation control. Navigation and control. That means, so for the navigation, the estimation rule is stable flight, whether your UAV is stable and is it following the autonomous path, what you have designed by you, or it is following a random path. So stability of your flight is one of the parameters during the navigation of your UAV communication. So stable flight and navigation path. Then, so if you remember the cooperative communication, so if two mobiles are cooperatively communicating from the base station, then from one mobile to another mobile, there is some synchronization. Is one of the major parameter has to be established. That means the clock time of the mobile 1 and clock time of the mobile 2 must be synced together. Then only the synchronization between these two mobiles are happening and we can happily receive your signals. Next one is interference management is another problem. So when so many UAVs are communicated, UAVs are on the ground, UAVs are placed in the space, then so all the UAVs are transmitting their signals. So the UAV1 information and UAV2 information when they are close to each other, so the transmission has some interference between because of UAV2 is acting as an interference to the UAV1. Similarly, UAV1 is acting as an interference to the UAV2, right? So this is very much important in UAV communication. So interference management is one of the parameters. We have to make it a proper management system so that you have to adapt your power control and scheduling of your parameters. Then simultaneously interference management. Okay, so like that we can adopt these values, and also some emerging research directions if you wanted to ask in UAV communication. So maybe AI estimation is another extension for estimation theory and foundation. So nowadays the buzzword is artificial intelligence. So AI aided estimation. So that means your deep learning based channel and position estimators, joint communication and sensing, JSAT, joint joint communication and sensing, JCAS. So that is simultaneous data transmission and environment estimation. Both are happening in joint communication and sensing, and distributed estimation in UAV swarms. There are some visual fuses, etc. are to be estimated. Okay. So now, first we start with estimation theory foundations. for about some half an hour time. We spare some half an hour time on estimation theory foundations. Then we apply this estimation theory for EAV communication. So in this EAVs, why actually the estimation theory is very much important is estimation is fundamental because it is a fundamental theory for channel estimation, localization, navigation, targeting, and spectrum sensing, and how to formulate your estimation problem. Okay, so I start the basics. I start the basics of estimation theory. So this basic that means so your y just give me a moment. So when you are doing the parameter of estimation, we have to first measure its performance. Any estimator you design, you have to measure its performance. So we take one simple example of an estimator, then how to measure its performance. We'll compute and we'll apply this performance measure for your UAV communication. So assessing the estimator performance. So one of the key component of estimator performance is to talk about performance of an estimator. Okay. So let us take x of n is a plus w of n. Okay. So where w of n is additive white Gaussian noise at nth sample, and there are such samples are available from 0 to n minus 1 samples are available. Okay. Now I have to design an estimator for estimating the value of a, because a is hidden inside your additive white Gaussian noise. So one example is I am saying that a is we are sending for a duration of 10 seconds. Let us t equal to 10 seconds and amplitude a is equal to 10 volts. We are sending this information. Then what is happening? It is added by additive white Gaussian noise. So when it is added by additive white Gaussian noise samples, so of different samples, your value of your received signal looks in this fashion. Why? So this is your x of n after adding your additive white Gaussian noise. So by looking at this observation, I should able to say I should design one estimator. That estimator should give me the approximate value of A that was transmitted. That is 10, right? So to propose this kind of an estimator, first we have to design an estimator. So the design of an estimator is not. So one simple estimator is sample mean estimator. Sample mean estimator. So what it does, the sample mean estimator is just that means estimating the parameters. So generally we give the notation as a cat. So what we do, because we add all the samples of n number of samples we have received, and we'll add all the samples and we normalize with 1 by n. So if you are receiving 10 samples, we add all the 10 samples and divided by n. That is called an estimator. So this is my estimator. So this estimator is one kind of an estimator. Maybe another estimator also I'll design. What is the estimator? So I'll give another notation for the estimator, reverse cap. So in that reverse estimate, I'll just take only one sample of information. I'll say that this is my approximate value of A estimate. Okay. Then do the comparison between A cap and A reverse cap. So which is giving less variant, because if you look at the waveform, if you look at the probability of receiving of your x of n when it is added by additive by Gaussian noise, right? So how it looks like, it has to be, that means any if it w of n is an additive white Gaussian noise, and the mean value is here we are taking it as 10. So around 10, it is the probability is added. This is called the probability of x given your x, right? This is the probability of x received. So this is like a Gaussian PDF, but it has a mean value of 10. Okay. Now, if this variance is large, this is called X sigma square. So some PDFs where when you are receiving the signal of the same nature, where this variance is, I'll call it as sigma 1 square, I'll call it as sigma 2 square. So when you are designing your estimators, so suppose the estimator A cap is giving this much of variance of sigma 1 square. A reverse cap is giving the variance of sigma 2 square. Then definitely it was less variant. So that means all the time the value to be estimated is slightly varying from 10 to a smaller range, right? But whereas in this case, from 10, so because this is your sigma square, so the range of variance are more. Let us take this one as 15 and minus 15, something like that. But whereas in this case, maybe it is deviated to 12 and minus 12. Okay. That means your estimation value will lie between. So from 10, it is deviated to maximum value deviation is 2. So it may be go to up to maximum value of 12, or from 12, it may go to minus value of minus 12. So deviation in this case is roughly a 4, but deviation in this case is roughly 10, right? So that because it has the more variance, then I would say that definitely the second estimator is the better estimator than the first estimator. This is the performance measure. One of the important approach what we follow in estimation procedures is the performance measure of an estimator. So we measure the performance of the signal. That means we have to compute variance of your A estimator and also variance of your, suppose if you are proposing another estimator, you have to calculate variance of A inverse of that A estimate. So suppose variance of A estimate is much greater than variance of A inverse estimate, definitely we will adopt this kind of estimation. What is that estimation? Is only taking simple value of only one sample of information. Okay. So is the flow is correctly going, or is something is understanding because I rarely use PPT. I always like to see that
Yes, madam. Yes, madam. It's going
it's
in.
okay. Okay. Right. Hmm. So we have to measure the performance of the estimator. Now, this estimator is actually one kind of a random variable, right? So then after computing, after proposing an estimation formula, one formula is summation formula. Another formula is take one sample. Maybe you can propose another estimator where I'll take average of two samples, maybe x of 0 and x of n minus 1, first sample and last sample, and take the average. Suppose like that, you can propose many estimators. So for all the estimators, we have to compute their variance. Based on which one is giving the better variance, then that is to be adopted. So that means we have to justify your meaning of estimation using minimum variance and unbiased. Minimum variance and unbiased. What do you mean by unbiased? Minimum variance, unbiased estimation. Any estimator you design, that must be a minimum variance, unbiased estimator. So we call it as MVU, minimum variance, unbiased estimator. MVU estimator. So it should have a less sigma. Sigma must be a smaller value. And also suppose I am estimating A. So it has to be estimated towards A, but not biased to some other value. That is the meaning of unbiased estimation. Okay. So we'll deep into the unbiased estimator. So estimator, suppose a parameter theta I am estimating, right? So the theta range is between A to B. This theta lies between A to B. Now I have proposed an estimator, theta estimate. So this theta estimator may be sample mean estimator. This is one of the estimator. So n equal to 0 to capital N minus 1 x of n. So from this, after summing up all the samples of the signal, the parameter what is hidden inside. In our previous example, it is y equal to a plus w of n. Then a the value we are estimating. That means your theta equal to a estimate, right? So this when you are estimating the theta, minimum variance and unbiased. So unbiased meaning, so this estimated unbiased means on the average, estimated will yield it to on the average value. What is that? Suppose on an average, if you are computing the estimated value, then it must reach to its original value. It must reach to its original value. That is called unbiased estimation. So I did estimation theta estimate and I computed by taking n equal to some 100 samples. I estimated theta. Okay. Now again you take some more new set of data. Again you take some another. So that means first time I have estimated at theta estimate. Then this is the first time. Again you take 100 samples of data. Take second time also you do the estimation. That is, I'll call it as theta 2. Like that, for 100 times, I'll take 100 samples of each and I'll compute the value of the estimate. Take average of all these estimates. What do you mean by average? Average is nothing but expected value of theta estimate. Then if you take average of all these estimates, it has to reach to its original value. This is not of either value. That is called unbiased estimator. It should have a minimum variance and unbiased estimator. Okay. So your sample mean estimator to become an unbiased estimator. So we generally plot the PDF graph A, and that is the probability of A estimate, probability of your A estimate along the axis of A, along your axis of your A estimate, the mean value is around A. So that is normal distributed with mean A and how many samples we have taken? N number of samples. So sigma square by N. So this is the probability density function for sample mean estimator. This is the PDF graph, PDF of sample mean estimator. So like that means the expected value of theta estimate equal to theta for all values of theta. Any value of theta, that is, suppose in this example, A equal to 10, A equal to 10, A equal to 20, A equal to 30, any value of value if you are estimating, that has to reach to its original value only. Then it is called unbiased estimate. Okay. So this unbiased estimated procedure we have to adopt. Then variance of this estimator. So on an average, so estimators are unbiased, same variance and uncorrelated with each other. Okay. So that means variance of your theta estimate. So this variance of the theta estimate, I want to compute. So what is the sample mean estimator? If you remember your equations, this is your estimation formula, right? So for this estimation formula, I want to compute its variance. So the variance of the sample mean estimator is becoming how to compute the variance of this estimator. That is 1 by n summation of n equal to 0 to n minus 1 x of n, right? So this is giving me the theta estimate. This is giving me the theta estimate. Now I want to compute variance of this estimate. So variance of this estimate becomes actually, so because we are normalizing with respect to n, then when upon the computation of variance, it becomes n square. So I will write it as 1 by n square times summation of those values of I equal to some 1 to L x variance of your theta I estimate. The overall, because 100 times you are computing, because sample average mean equal to theta. So 100 times you are computing the theta and you are taking the average, then it is related to theta. That means variance will become So those 100 times, that means that n, and then is your 100, so it becomes 1 by n square theta estimate. So this will give me how many times? Suppose it is this summation we are doing for n number of times. Then n variance of this is because summation theta I estimate by n square will become variance of your theta I estimate by n. That is your average. More estimates are arranged, variance will decrease as n is increasing, right? As n is tending to infinity, your theta estimate will approximate it to original value of theta. That's the meaning. So estimators are unbiased, meaning we will write. So if it is unbiased, suppose the estimator is biased, how the equation is to be written. So theta I estimate is actually it is theta only, but if it is biased, that means some function of theta. This is called biased value of biased value is added to this. Okay, so some theta value is estimated to this. So now theta estimate, what is the average value of this biased estimator? If you compute, so that means if you apply the expectation on both sides, so this is summation value expectation and each theta estimate. So it will give me the value of theta plus b theta. So this b theta, b of theta is actually its average value of theta estimate minus theta, original value of the resistance. Then we compute the mean square error of your theta estimate, MSE of theta estimate. That is actually original expectation of theta estimate minus theta whole square. It's the mean square value of the theta estimate. So these are the some of the basics which are required for your estimation procedures. Okay. So now not only one parameter estimation, there are multiple parameters. Generally in UAV communication, you have to estimate position. That means X, Y, Z. 3 parameters you have to estimate. Not only height. So height, width and length. So where it is located, 3 parameters have to be estimated. That means your theta is actually a vector parameter. So theta 1, theta 2 up to some theta n transpose. So this is how we write the parameters. Then how many parameters I have to estimate? Theta estimate is theta 1 estimate, theta 2 estimate. So like that I have to estimate some theta p parameters I have to estimate. Okay. So with these fundamentals, then the estimation accuracy we know very well. So just we talk about Cramer-Rao lower bound, CRLB. CRLB, Cramer-Rao lower bound. So this Cramer-Rao lower bound is a scalar parameter, some value, where the PDF, we take PDF, that is the probability of X theta. It is intended with theta. The value of theta is written in your X. That is the probability of X comma theta. It has to satisfy. The probability of this function has to satisfy the regularity condition. So what is the regularity condition? That means expected value of generally your probability values. So before going to the CRLB, I'll note down the importance of the probability. So y is equivalent to x plus n, suppose. In our case, x is equivalent to a, that is value of 10. Okay. This is additive word Gaussian noise. Then y minus x is your additive word Gaussian noise. Right? Received and transmitted. This is your equivalent to your, if you subtract both of them, the remaining value is only noise. Then we know the noise probability density function and with a zero mean and varying sigma square, right? That means what is the probability of y minus x? Is nothing but the probability of n. So how do you figure out this probability? That means f of x f of n is 1 by 2 pi sigma square e power minus x minus its mean whole square by 2 sigma square. Generally we write if x is a random variable, we subtract with mean and divided by its variance, right? So this is the noise PDF. But whereas in our case, we are doing the samples with respect to samples x of n. N is running from 0 to n minus 1. N number of samples are there. And each sample is independent. So when each sample is independent, what is a joint PDF? We have to compute the joint PDF, probability density function. So what is a joint PDF? So this joint PDF, because they are uncorrelated, that means in your x of n, we have x of 0, x of 1 and x of n minus 1. Right? So what is their joint PDF? If anybody asking, it is nothing but, so it is nothing but f n of n, simply we write f n of x naught multiplication with f n of x1 and upon f n of x of capital N minus 1 multiplications. So we do the multiplication. That means, how do you write? So this one simple distribution is this e power minus, right? So such, how many are there? N numbers are there. So each is having the same variance. That means I can write the example as 1 by 2 pi sigma square. How many such? Each one is having 1 by 2 pi sigma square under root. That means such numbers are n. So I can write n by 2. N by 2. And each one is having an exponential. So exponential for each x naught minus its mean whole square by 2 sigma square. The next one is x naught minus x naught x1 minus mu whole square by 2 sigma square. Such points, but they are in exponential format. That means in exponentially they add. So summation 1 by 2 sigma square summation n equal to 0 to n minus 1. For n you are writing, right? So n you are writing means y minus x whole square. This is the PDF distribution function. So using this PDF distribution function, we write, we expand what is the lower bound on your variance. What is the minimum variance which it cannot go beyond the variance value of a estimator what you are going to design. Okay. So by looking at this formula, because your data is hidden inside of your exponential format, which is not a linear one, it is a non-linear example, right? So this non-linear, you have to extract what is y minus x. It is not easy to extract y minus x. So for that reason, maximal likelihood principles we apply. What is the maximum likelihood principle? If you take ln of this value, if you take natural logarithm of this value, so natural logarithm, I will say this is one parameter, this is another parameter. So when I'll say that A1 and A2, so ln of A1, A2 is nothing but ln of A1 plus ln of A2, right? So these two values. So that means ln of A1, so ln of A1, so anyway, in this 1 by 2 pi sigma square to the power n by 2, there is no data is not present. It is common for all values. So generally we ignore this quantity. ln of A2. So when you take natural logarithm of an exponential, the value becomes simply inside the value, right? So inside the value means 1 by 2 sigma square summation n equal to 0 to n minus 1 y minus x whole square. This is your natural logarithm. So this natural logarithm value
Hello, madam.
ఒక 42 మెంబర్స్ ఉన్నారు.
కంటిన్యూ చేయండి.
ఓకే,
రికార్డింగ్ లో ఉందేమో ఒక్కసారి చూడరా అనుకోకుండా.
రికార్డింగ్ లోనే ఉంది.
సరేనండి, కంటిన్యూ చేయండి అయితే దయచేసి.
ఓకే, థ్యాంక్ యూ.
ఓకే.
Okay, sorry for the inconvenience. In between, there is a power cut. So
Okay.
finally, is my voice is audible?
Yes, madam. Audible, madam.
Okay. So I'm talking about CRLB, Kramer-Rao lower bound, because this is the fundamental value we have to compute. So this Kramer-Rao, so before going to the Kramer-Rao lower bound, I explained why do we take natural logarithm to your PDF, so that your hidden data in your expressions is coming out of from the exponential formats. Okay. So for that, we do these processes. Then, so by looking at, because to found this minimum variance parameter, your bound has to be said that your expected value of differentiation of natural logarithm of your probability of x comma theta, the theta we are estimating, by dou theta must be equivalent to 0 for all theta values. So this is called regularity condition. So it has to satisfy some regularity condition. So over this PDF, probability of x comma theta. So this variance of any unbiased estimator must satisfy. If it following this regularity condition, also it has to satisfy, then the variance of your theta estimate of the proposed estimator is always greater than or equivalent to 1 by minus of, because already one minus sign is there, right? So to compensate for the minus sign, we compute expected, this irregularity condition we put over there, but this irregularity is now 2 times differentiated. Dou square ln of probability of x comma theta by dou theta square. This is called Kramer-Rao lower bound. So the variance is always greater than this value only. It will not come below the Kramer-Rao lower bound. So if you compute, suppose for one value of the parameter, the Kramer-Rao lower bound is this one, then when you are designing an estimator, it will be always above this value. It will not exactly right, it will not go down of your Kramer-Rao lower bound. That's what he has designed, a formula. So this derivative is actually evaluated at the true value of theta, dou square ln of probability of x of theta by dou theta, and expectation is taken with respect to this probability. So this unbiased estimator may be found that it attains for all values of this theta. So minimum variance unbiased estimator, then we have seen the variance calculation. What is a Kramer-Rao lower bound? Using the second derivative of your the parameter values, and also the bound is dependent on theta in general, and we can compute the values of the signal. Suppose if time permits, maybe I can take one chart is there. Otherwise, voice is not audible. Okay. So we can compute the Kramer-Rao lower bound. If you are interested, I can because it consumes some time. You wanted me to give an example of how to compute Kramer-Rao lower bound? Yes. Okay. So then simplest example, because if you take UAV communication example, it takes long time. So I take only simplest example. So one example is X open, a general example is A plus W of n, and data vector is given for values of n minus 1. Okay, and W of n, its mean and variance are given. Mean value is 0 and variance is sigma square. So then we have to formulate what is the probability of A. Your theta is A. So probability of XA, right? So generally I said it is multiplication procedure, right? So in this formats, if you write, it is a multiplication. That means how many samples are there? N equal to 0 to n minus 1 samples are there. So each one is having sigma square, the same variance, and exponential of minus 1 by 2 sigma square times x of n, because we are bringing this x of n minus a equal to w of n. So we are writing the PDF for w of n. So it is x of n minus a whole square. This is your probability density function. So such n number of probability density functions you have to multiply for getting the final probability density function with the parameterized value of a. So then after that, so I said already we can write this expression as a multiplication. So 1 by 2 pi sigma square to the power n by 2 exponential value of minus 1 by 2 sigma square times summation of n equal to 0 to n minus 1 x of n minus a whole square. This is the product. All products are coming to n by 2 and exponential values multiplication is coming to summation. Now, first, we have to see first dou ln, right? Dou ln by probability of this x with respect to a, we have to compute. So, dou ln of probability of x comma a by dou a, that is a dou theta, right? Theta means a. Dou ln of dou theta. So, that means you have to apply dou by dou a of the above example. Ln and above example. Ln of this value, and then you have to differentiate with respect to a. So if you do dou by dou a of, first we take ln. So when you take ln, so 1 by 2 pi sigma square n by 2 ln of this, that means minus ln of 2 pi sigma square to the power n by 2. That's the first value, minus, because exponential ln is simply the value. So it is 2 sigma square summation of n equal to 0 to n minus 1 x of n minus a whole square, right? This is ln. After ln, we have to differentiate with respect to a. So if you differentiate with respect to a, anyway the a is not there, this is 0, only a is there in this one. So we can write this one as minus 1 by 2 sigma square. So it is whole square, that is summation of n equal to 0 to n minus 1 x of n minus a. This is your original value. So 2 times. So I'll write 2 outside. So this becomes x of n minus a, right? So this is your differentiation with respect to a. So I can write, I can expand, I can open this equation and I can write the values, what is after opening this equation. Minus 1 by sigma square summation of n equal to 0 to n minus 1 x of n is a one value plus n equal to 0 to n minus 1 a, that means n times a added. So it is minus plus, so n times a, right? This is all my dou ln of dou a. So if you take n as common, one value is a, one value is a, or n minus sigma square as common if you take. So then this becomes, this value is also with the minus n plus, this is also added with sigma square. So n by sigma square taken as common, then a, n by a, this term is over. Then the other term is simply n you are taking as common, but there is no n. So 1 by n summation of n equal to 0 to n minus 1 x of n, right? So what is happening now? This is nothing but your estimate, right? A estimate. This is your A estimate, or we'll call it as X bar. That means sample mean estimator. This is my sample mean estimated. Sample mean estimated is x bar. So maybe negative sign if we say. So then it is n by sigma square times x bar minus a. So actually I made the minus sign, minus also comes over here. So just somewhere I missed out. So this is my dou ln, right? Then again you have to compute dou square of ln of probability of x comma a by dou a square. Again one more time, if you do the with respect to a, then so anyway this has some value and only a is present in this case. That means it is independent of a, this parameter only dependent on a. That means finally if you do the differentiation with respect to a, the remaining value is n by sigma square, right? With some sign value is also there. Maybe somewhere I missed out that minus sign. So minus n by sigma square is there. Okay. So what is the dou square ln by dou ln is computed. So if you look at the Cramer-Rao lower bound, what I said, the variance of your theta estimate is always greater than or equivalent to 1 by with a minus sign expectation of dou square ln by dou ln square, right? So already we computed dou square ln by dou a square. For that we have to take average value with a negative sign and we have to divide by 1 by of that value. So if you do variance of your A estimate is always greater than or equivalent to, so right? So 1 by minus what is the expected value of minus expected values of minus n by sigma square. There is no random variable inside. That means 1 by only n by sigma square. That means we will say that this value is sigma square by n. See? So that means your sample mean estimated. This is my Cramer-Rao lower bound. CRLB per A estimate. So this is the variance. Always when you do your estimations, your estimation will give me a variance value always greater than or equivalent to at least sigma square by n for n number of samples. So this sample mean estimated attains the bound, right? And must therefore be the MVU estimate values, minimum variance unbiased estimator. So when Cramer-Rao lower bound is attained, so we can compute the other values and we can say that, so this value will say that Fisher information matrix. So variance of theta estimate is actually 1 by I of theta. So Fisher information matrix, a lot of the theory behind this you have to explain. So like that I can do some estimation of the signals. A phase estimation I want to do. So in your UAV communication, one important parameter is they transmit a sinusoidal signal 2 pi f naught into n plus a phase value of phi plus additional white Gaussian noise. Additional phase is added, right? So this phase estimation we want to do it. Then first we will find probability of x comma your phase estimation. We'll compute what is this. Then I find dou ln of probability of x comma phi by dou theta I'll find. Then I find dou square. After finding dou square, that value will be always greater than or equivalent to, the variance is greater than or equivalent to 1 by this minus expectation of dou square. So like that you have to compute your parameters, estimated parameters. Okay. Then till now are there anything is is it at least to some extent why we are doing estimation of a parameter, or how to propose a estimator? If you are proposing an estimator, what are the parameters have to be calculated to measure the performance of the estimator, and what is a Cramer-Rao lower bound, right? We understood the meaning of a Cramer-Rao lower bound. So like that you can extend the parameters. Sometimes the parameters are hidden in other formats like sine and cos. So in the previous example, if you look at the parameter, what you are estimating is embedded inside your cos, right? So it's not a general direct formula. It is embedded inside the cos. So that means there are some transformation of the parameters are also happening. Then suppose alpha is equivalent to g of theta. It is given with the function. G of theta means given with the function. So such cases, how to compute the Cramer-Rao lower bound? So we have to follow certain procedures to compute the parameter value of Cramer-Rao lower bound. One example of these kind of a parameter. Suppose the parameter what you are estimating is y equal to a plus w of n, right? So earlier we estimated a, the amplitude of the signal. Now this time I want to compute SNR, signal to noise ratio estimation. SNR estimation. That means signal power by noise power I have to estimate. So before going to that, first I have to estimate the signal power. Signal power means what? It is A square, right? So earlier we estimated A. Now we have to estimate A square. So that means your alpha is equivalent to A square. This is a function. Or sometimes, so A, and sometimes I want to estimate the value as 4A. Then your alpha equal to 4A. This is transformation of the parameters. So for the transformation of the parameters, so we have to do from scalar parameter to multi-vector parameters, and then we have to adopt your procedures for computing the parameter estimation. So in such cases, your variance of your estimator is directly we can write as a function of theta. As a function of theta is always according to your procedures, dou of g by dou theta whole square divided by Fisher information matrix I of theta, right? So like that, we have to compute. What is this Fisher information matrix? I said we computed this Fisher information matrix from the Cramer-Rao lower bound. That means it is always greater than or equivalent to dou g of theta by dou theta whole square multiplied by the variance of your theta estimate. So now earlier variance, when the parameter is transformed parameter, it is multiplied by another factor of differentiation of the vector. So that means a square. What is the differentiation? 2a, right? So it is multiplied by, in this example, 4 dou theta by a. So that means 2a. This becomes 4a. 4a square and variance of theta estimate when the signal is transformed. So that means generally we call it as a square times variance of theta estimate. Okay. Like that, the efficiency is measured and the parameters are measured. Now, so we are moving to the next procedure, the vector parameters. Similarly, we can extend for the vector parameter estimation. We can attain the Cramer-Rao lower bound. Next example is some modeling of your data. Suppose, simplest example we take. X of n is A plus B n plus additive Gaussian noise. N is running from 0 to n minus 1. Okay. So this looks like y equal to mx plus c, right? Y equal to mx plus c. That means this is an intercept. This one is intercept. This one is the slope. B is your slope. For that signal, some additive Gaussian noise is added. So generally what we do, we propose some models, linear models, when a signal format of this nature. Generally in speech processing and in also in your position estimation, we use these linear models. So generally what we do, we write your example in the vector form x is equal to h theta plus w. We write in this format. These are all our vectors now. All are in vector. So what is x? X is your data. That means x of 0 to x of n minus 1 transpose. Generally we represent a vector in column format. So x0 to x of 1. That means so my x is n cross 1. Only one column, n rows are present in this vector x. Then w is also n cross 1. No problem. Because w is your w of 0 to w of n minus 1 transpose. Okay. So w of n minus 1 transpose. So for this model, a plus bn, x of n is written, w of n is written, a plus bn. So this a plus bn also we want to put them in the vector format for n is running from 0 to n minus 1 data samples. So generally what we do, so a plus bn, it means, so if you see the expansion a b equal to 0, then only a will be there. For n equal to 0. For n equal to 1, a plus b. For n equal to 2, a plus n equal to 2. So 2b, right? So then a plus 3b. Like that it goes up to a plus n minus 1 times b. This is the signal what we are receiving for each sample. So that means we will propose a vector to represent this one and such that your data vector is modeled as in the vector format. So what we do, we write in h theta. So what are the parameters we want to estimate? A and B are the parameters, right? So that means your theta is A, B transpose. So that means it is formulated like this, A and B. Now, we have to propose a value of x such that upon multiplication with h into theta will be your total data sample of A plus Bn format. So we are proposing a h. So first time it is A and B is 0, right? So 1, 0. Second time again A, B. The multiplication factor of B is 1. So 1, 1. So like that, for all values of A, it is 2. So it goes up to 1, n minus 1. This is my H matrix. So this H matrix is becoming now n cross 2 vector. Okay. So now if you look at how H multiplied by theta, how it looks like, H multiplied by theta is 1, 1, 1, 0, 1, 2, up to it goes up to n minus 1. Theta, what is the theta? Theta is AB, AB, right? So if you write this model, first A, then 1, 1, A plus B. Then like that it goes up to A plus n minus 1 into B format. So we could able to model our data for all values of data vectors as x is equal to h theta plus w, right? This is the vector representation. So this is called a linear model. This is called a linear model. So by defining the linear model, we assume that noise vector is Gaussian. Okay. So determination of for this data model, our next procedure is minimum variance unbiased estimator we have to propose. Minimum variance unbiased estimator if possible, is possible if the equality constraints of Cramer-Rawlins theorem are satisfied. Okay. Then we have to do the theta estimate. So this theta estimate is nothing but your function, that is g of x. So first we have to compute dou ln of probability of x comma theta by dou theta. So this we have to compute. That is equivalent to, it is in the form of Fisher information matrix into g of x minus theta format we have to propose, right? So then dou by dou theta. So first First, I am proposing what is probability of x minus theta in the vector format. So otherwise, we will write for the whole equation. Dou ln of probability of x comma theta by dou theta. So if you write for this equation, dou by dou theta of minus ln of, because 2 pi, right? So 2 pi sigma square to the power n by 2 minus 1 by 2 sigma square. The data model, how do you write? In the exponential format, x minus h theta transpose into x minus h theta. X minus h theta. So look at the equation. X equal to h theta plus w, right? So this equation we are writing. That means x minus h theta is equal to w. I know the PDF of w. Additive white Gaussian noise. We are imposing the signal as x minus h theta. But you have to, if you remember, exponential of minus x minus value whole square. So in the vector format, how do you do whole square? Transpose into original value will become a whole square. So this is your model. Now you have to differentiate with respect to theta. So upon differentiation with respect to theta, anyway this is independent of theta, we can ignore it. Only dou by dou theta will goes to this value, right? So when you do dou by dou theta, so before going to dou by dou theta, so we will expand, we'll ignore this component, we just rewrite 1 by 2 sigma square times transpose vector. So right, so transpose vector, how do you write? X transpose minus h theta transpose, right? That means theta transpose h transpose. This value is multiplied by x minus h theta. X minus h theta. So upon opening this signal, this multiplied by this. So dou by dou theta of minus 1 by 2 sigma square times x transpose x, one value, this multiplied by this, minus x transpose h theta, x transpose h theta, minus this multiplied by this theta transpose h transpose x, minus minus plus, that is theta transpose h transpose h theta. Okay, next we have to do the differentiation. So upon doing the differentiation, the value of minus 1 by 2 pi sigma square can be brought outside. Now apply dou by dou theta. What is dou by dou theta for this one? So first one is independent of theta, so it is zero differentiation. Next, x transpose h theta dou by dou theta. Dou by dou theta of x transpose h theta. So what is the value of x transpose h theta? So if you write, okay, so that means the remaining value from this differentiation x transpose h, and also this one if you compute, this one is h transpose x. This is with respect to theta transpose. So upon modifications of these two, this becomes 2 times h transpose x plus this one. There are 2, that means theta square. So 1 theta will remain. So 2 h transpose h theta. Okay. So like that we compute. Then, so if you multiply with a minus sign, 2h transpose x minus minus plus minus 2h transpose h theta whole by 2 sigma square. That means dou ln of dou theta value is this. Dou ln of dou theta value is this. Now, so 2 to anyway also we can cancel out, no problem. So this is your dou ln of dou theta, right? So this dou ln of dou theta, if you make it to 0, then I can extract my theta estimate. So upon making it to 0, this goes to other side. So what to extract only theta, h transpose h is there. I have to multiply this h transpose h with inverse of h transpose h, right? So that means we are taking h transpose h as common, H transpose H as common, then I can write the value as, so I have to multiply with inverse, H transpose H inverse into original factor H transpose X as it is I am keeping here, minus this one is H transpose is taken outside as common, then remaining value is only theta, right? So this is the value. Now you make it to 0 and tell me what is the theta estimate. So this theta estimate, other side it goes, then so when I'm making it to 0, the theta estimate will be H transpose H inverse H transpose X is your theta estimate. So like that, for a vector parameter, we propose the model based on the given model. We propose the theta estimate. So generally in your channel models also, we invert the channel and multiply with the transmitted signal, such that we can estimate your values. Okay, so that means this H trans and sigma square is also present, right? So this value of your theta estimate, this is called the previous value. So H transpose H by sigma square, one parameter, right? This is called I of theta, Fisher information matrix. Like that you can extend for your, based on the model, we propose an estimator and we also propose that it is a minimum variance unbiased estimator and what is the theta estimate of that proposed estimate. And is it attaining the Cramer-Rao lower bound or not? Also we compute. Okay. So we can extend these analysis for your position estimation, tracking of your target estimation, frequency estimation. So because in UAV you are communicating with a particular frequency and you are going to change the frequency of your transmission. Then what is the correct frequency you have transmitted? So that parameter we need to estimate. So you have to estimate such parameters in real time. So just so in some cases, just I'll take 2 minutes break, I'll drink water and come back. So next, going further on estimation problem. So Cramer-Rao lower bound tells us it is an efficient and MU estimate. Okay. So for your linear models, Cramer-Rao lower bound exists and we have designed an MU estimator. So efficient estimator, it does not exist. But still we are interested to find minimum variance unbiased estimate. It's not efficient, but we want to find the minimum variance unbiased estimating. Okay, so need some statistics and important using the Blackwell-Lehman-Sheffe theorem. We can find such estimators, some unbiased estimators, and their performance we can compute. Moving on to the factorization formula and all, we have to establish a procedure. So what we learned till now, all unbiased estimators. So like your linear estimator, just now we are proposing the vector format. So this is the minimum variance unbiased estimator. And non-linear, some estimators are non-linear estimators. Some estimators are linear estimators are exist. Okay. So but for any estimator, the funda behind the estimation of your signals is its probability density functions. Right? That is important. Suppose, is there any other way of coming out from the probability density function? Can you propose a maximally equal or likelihood estimation? ML estimate, maximally maximal likelihood estimation. ML estimation, it is also called ML. Maximum likelihood estimation. Okay. So what we do, we investigate some alternative to the MU estimators. Some situations where the MU, minimum variance unbiased estimator, does not exist and cannot be found. Even if it does exist also, you may not be able to find MU estimator. This is based on the some maximum likelihood principle. For practical interest also, the performance optimization for large data records. So approximately MU estimated due to its inefficiency and all. So we do some practical estimators based on the maximum likelihood estimation principles. So what is this practical approach? ML estimation practical approach is, so earlier also we have given the probability density functions of x comma a, and we computed dou by dou a of ln of that probability of x comma a, right? So then what we did, we computed it dou square, then the variance is computed. So much of procedure is done. But in practicality, we just see that the maximally likelihood principles, based on the maximum likelihood principles, then can do some estimation procedures. Okay. So if you remember this dou ln of p of x by a, already we computed values where we have executed for some parameter values. So one example earlier also we have taken a plus w of n, and a value is positive always. Okay. So for this a value is positive. So in this case, what we are proposing is W as the variance of sigma square. Okay. And the A value, suppose the variance of W of n is sigma square, and if that value is equivalent to your actual original value of your estimator, what you are estimating? You are estimating A. The variance of W of n is equivalent to A. Then what do you do? Right? So if you write the equations for this equal value of 1 by 2 pi sigma square. What is sigma square now? Is A. Right? So this value is given inside, and exponential of minus 1 by 2a summation of n equal to 0 to n minus 1 x of n minus a whole square. This is the value, right? But what is happening now? The variance is equivalent to a. The variance is equivalent to a. Then upon doing dou ln, so if you do compute dou ln by dou a, so what is happening? Dou ln by dou a, this is also dependent. This factor is also dependent, right? So if you write for these formulas, directly if you apply dou by dou a, then a in of n by 2, that means n by 2 outside, because ln we have computed. So that means this becomes n by a and minus n by a plus 1 by 2a summation of n equal to 0 to n minus 1 x of n minus a, right? And plus 1 by 2a square, because summation of n equal to 0 to n minus 1 x of n minus a whole square. So now this dou ln is computed, right? So it is an unbiased estimator can be found that attains the bound for all values of theta if and only if this follows some regularity conditions. So if we, then that means we should be able to write this dou ln as I of theta multiplied by g of x minus theta format. So where in this case it is a complicated expression. This is a complicated expression. So I cannot open this one as multiplication of variance multiplied by into this format. Okay. So when you are unable to write into that format, that means there is no efficient estimate that exists. No efficient estimated exist. Then what is the other principle? When there is no efficient estimator exist, so we have to follow certain other procedures for computation of your computation based on maximum likelihood principles. So this maximum likelihood principle is very simple. We first find the probability, and after finding probability, we find ln of probability of x comma a. Then simply we differentiate that dou ln of probability of x comma a with respect to dou a. Then simply we make it 0. Because earlier we have seen I cannot write into the specified format. That means minimum variance unbiased estimate does not exist. But even then I want to compute an estimator. I want to estimate a parameter. So then in that such scenario, simply make it 0 and compute your estimated values. Okay. So for the same example, if you extend that computation for this one, dou ln of dou a and make it to 0, that means this value, if you make it to 0, so we can give the value of the signal after doing lot of procedures, after expanding the whole equation. Your a estimate has become, I am not writing whole because we will see some other formats. So it becomes minus half plus root n summation of n equal to 0 to n minus 1 x square of n plus 1 by 4. It translates into this is the estimation value using the maximum likelihood principles. Okay. So that means what is happening? It is added with some bias 1 by 4 and anyway under square root of x square of n, right? General estimate is 1 by n summation of n equal to 0 to n minus 1 only x of n. This is square root of x square of n 1 by 2 and I also added with some additional factor. So based on the maximum likelihood principles, because the sigma square variance of your relative white Gaussian noise is equivalent to the value of the parameter what you are estimating, then in such cases MVA estimate does not exist. Then what is the best procedure? Apply maximum likelihood principles. So from the principle, estimate your parameters. This is called maximum likelihood estimator. Then the next one is least square estimates. LS. So least square estimate. So like your, maybe it is optimal or nearly optimal estimator, I cannot say, unbiased estimators and a minimum variance estimator. So here the advantage of least square estimators is we don't need any probability assumption at all and are made about the data. Only signal model is assumed. In the least square estimates, no probability is required. No probability assumptions, only signal model is important. In least square estimates, only signal model is important in the least square estimates. So this least square estimate, the signal model we have to propose and make it square, that must be minimum value. So we apply same least square to the same example of A plus W of n least squares principles. So this is A has to be estimated. So I'll write some J is equivalent to summation of n equal to what, n equal to 0 to n minus 1 x of n minus a whole square. Right? That is our W of n formula. Then for this dou J by dou A, just I compute. So upon computation of this value, this becomes minus 2 summation of n equal to 0 to n minus 1 x of n minus a. Right? So we just make it to 0. We just make it to 0. From there, I found estimate. Very simple. Least squares is the very simplest example. So then it becomes 1 by n summation of n equal to 0 to n minus 1, n minus 1. So that is the estimate upon making it to 0. So this is equal to your sample mean estimate. Okay. So but we cannot claim that is an optimal in the minimum variance sense, but it minimizes the least square. There is only one advantage. It minimizes the least square. We haven't targeted about what is the probability of the solution, what is the probability of your equation and all, doesn't matter for us. Just what we do, we formulate the value. Suppose some signal S of n is cos 2 pi f naught of n, estimate f naught. Okay. So in that, I formulate the equation Joe of f naught. What is my Joe of f naught? I sample square n minus 1 times my x of n minus its original value. That means x of n is equivalent to cos 2 pi f naught of n plus w of n, right? Plus w of n. So I am writing x of n minus cos 2 pi f naught of n is equivalent to w of n. Least square. So I am making it as square. That means cos 2 pi f naught of n whole square. Then I differentiate with respect to the parameter what you are going to estimate. That means j f naught dou j f naught by dou f naught. So with respect to f naught, dou by dou f naught of the above value, I do differentiation. And I'll apply to 0. I'll say that this is my estimate. But you cannot claim that this is a minimum variance past estimated and attains Cramer round overboard. Okay? Those procedures you cannot problem. So it is a quadratic equation now. So quadratic in one some amplitude also. So amplitude and frequency. Suppose you are estimating A, then we'll fix other one as constant. So then we estimate A. Later we put that value of that estimate A into the equation. Then we estimate F naught. If you are doing two separate parameter estimations. So least square estimates. Then, so least square estimate also can be extended to your data models, like your linear model in the previous case. Suppose x is equivalent to h theta plus w. So then in that case, x minus h theta, right, equal to w. So what is the least square? I have to apply x minus h theta square I have to make. Transpose into x minus h theta. This is the square object, right? So this square object, after making the square, I have to differentiate with respect to. So first we'll open the square, then we differentiate. So that means x transpose minus theta transpose h transpose into x minus h theta. So upon opening x transpose x minus x transpose h theta minus theta transpose h transpose x minus plus theta transpose h transpose h theta. Okay, this is your square term. So this square term we have to differentiate with respect to dou by dou theta. So upon differentiating dou by theta, this is 0 and x transpose h theta differentiation, theta transpose h transpose x differentiation, then the square differentiation. So I explained earlier. So this becomes both are same upon differentiation. So it will result into 2 times H transpose theta minus is equal minus plus 2 times H transpose H theta. Okay. So then what is the next one? So we have to make this solution as 0. Simple, very simple. So from there I explained earlier also, that is H transpose H inverse, H transpose X is your theta estimate. Okay. So least square estimate is very simple estimator. So then another kind of estimator, MMSE estimator, recursive least square estimators. Also we can propose constrained least square estimators. So in between I can constrain the value of some C in between. You can propose. And also we will apply transformation of parameters to these estimators. So on, so that you can extend the another approach is the Bayesian philosophy. Okay. MMS estimated. So this Bayesian philosophy is actually a classical approach to our statistical estimation. So it is theta is deterministic. Suppose the value is deterministic. It's not a random signal. Deterministic, but unknown to us. Okay. So statistical means beta assume a random variable. Okay. So it is deterministic but unknown. We have used MU estimator, least square estimators, and other kind of constrained least square estimators. Okay. Best least square estimators and all we applied. Suppose this theta is now assumed to be a random variable. Theta is now a random variable. So we don't know, we cannot know the value of theta. It's supposed to be, always it is random. Sometimes the value is 10, sometimes it is 100, sometimes it is 20. But irrespective of its nature, I have to estimate that parameter. If the received value is 20, then I have to estimate this 20. If it is 100, 100. If it is 10, 10. Okay. So that means it assumes some statistical approach. Particularly, this follows a Bayesian approach. So that means if some prior knowledge about theta is available, what is the prior knowledge of? Because it's when I'm saying it is a random variable, what is the probability, particular probability density function of this random variable? If it is uniformly changing between some minus 10 to 10, right? So it uniformly changes between this value. Then I can predict that somewhere when I am doing estimation procedure, maybe sometimes minus 9, sometimes plus 9, sometimes 0. Like that, we can estimate the value of the signal. So because it is a random variable, it can lie between any of this range. So now, so Bayesian approach is used for when the estimation parameter what you are estimating is a random variable. Till now we have seen deterministic signals. So that means prior knowledge of the estimation is very much important. So what is the prior knowledge of the estimate? When it is important, how to calculate? So that means the probability value of x on A is can be written as probability of A given x into probability of x, correct? That means the total probability of random variable x, A given x is the probability. So from this probability density functions, Bayesian mean square error. Bayesian mean square error of by a estimate can be computed like Bayesian approach. So it is an integration. A minus A estimate whole square and its probability. That is, what is the probability of A given X, dA into probability of X dx. Right? So if you apply this procedure, we can find using the Bayesian approximation method. So we need to derive many values. That means, but how do you find probability of A given X? Using the Bayesian approach. So the probability of A given X is nothing but the probability of X given A into probability of A by probability of X. Right? This is something prior knowledge is known to you, then the posterior probability can be computed based on this probabilistic methods. And next we can go to the Coleman. Time is not sufficient. Otherwise, we can go to the Coleman schedule. And spectrogram estimations. So like that, we can extend. So nowadays, the buzzword is your AI models. So all your AI models are based on probabilistic approaches only. Okay. So with this, the floor is open for some questions because we cannot complete the whole theory of estimation in 2 hours. Just I gave a flavor how to start your work for your estimation theory of your parameter estimation. Just I gave a flavor of the approaches what you have to follow and how many kinds of estimators, what are the performance of, how do you measure the performance of the estimator, what are the parameters measured, are you estimating a deterministic signal or a random signal? Based on that, you have to apply your techniques and we can extend your estimation theory for any kind of a communication, any kind of an object detection procedures. So now the floor is open for some questions.
Participants, if you have any questions, please ask. Yeah, someone is asking question, I think. Sorry for disturbing. Please ask. Please carry on. Please carry on. Sorry for disturbing you. Please carry on. Yeah, someone was talking before. Please carry on.
I think Nageshwar Rao.
Yes, madam. It's me only, madam.
Okay.
Yeah.
ఎవరికైనా క్వశ్చన్స్ ఉన్నాయండి? Yeah, you are having any doubts? Participants, Amma.
It becomes Greek and Latin for them.
Huh?
Short term, but lot of information you have shared, madam.
Yeah.
Yes.
It becomes a Greek and Latin because it is not a PPT presentation, no?
Yes, madam. Actually, and also mathematics and somewhat understanding is somewhat difficult. If they have clear knowledge, then they will get some doubts.
Yes.
But talk is very good, madam. It is how to, what is the importance and everything is very clear.
Yes. So in every aspect of communication, detection and estimation theory, one of the fundamental course.
Yes, madam. Yes.
So anyone
Actually,
is
here, MTech students are there, madam. They have the course. They are listening actually.
Our MTech students?
From Siddhartha also, madam.
Okay. So Nageshwara is our student, Kalpana?
నాగేశ్వరరావు తెలియదండి.
K. Nageshwar Rao.
Madam, yes, madam.
Nageshwar Rao. Yeah, he was my student.
Okay. Where are you working now?
Siddhartha, madam.
Siddhartha. Okay. Okay.
Thank you, madam. Thank you for your wonderful
Yes.
lecture.
It's not wonderful. It is very boring.
Actually,
because
this topic
mathematics,
no one will teach, na, madam.
Yes.
And some of the faculty are also asking for recordings of this lecture.
Mhm. Okay. No problem.
Yes,
Because anyway, screen recording you have done, no?
Yes, madam. Yes,
Help
madam.
now. You can share with them.
we'll share with them. Okay, no problem.
Yes, no problem. Some mistakes here and there when I'm writing the equations may happen, but yes, the approach they can follow.
Yes, madam.
Okay.
Okay, madam. Okay, madam. Yeah, then we'll stop here, madam.
Yes, madam.
Yeah, okay then. Okay. Thank you, madam. Thank you, madam.
Yeah, thank you, Kalpana, for giving me this opportunity. So once again, I thank you all the participants for patiently listening. And also those who did not register for PhD program, please do register with NIT Warangal.
Okay, madam. Thank you, madam.
Thank you.
Thank you. Thank you. నాగేశ్వరరావు అయిపోయిందండి వాళ్ళకి లెక్చర్ సెషన్ అయిపోయింది. రేపు మార్నింగ్ ఎప్పుడుంది? 10 o'clock ఉంది కదా.
Yes, madam.
రేపు మార్నింగ్ 10 o'clock కమ్మట్ చేస్తారు.
Okay, madam.
సరేనండి. రేపు మీకు కరెంట్ వచ్చిందండి?
Yes, madam.
సరే, రేపు మార్నింగ్ 10 o'clockకి కలుద్దాం అయితే.
Okay, madam.
కొంచెం పార్టిసిపెంట్స్ రమ్మని చెప్పండి. ఐ మీన్ వాళ్ళు ప్రాబ్లమ్స్ లో ఉన్నారు.
Yes,
ఓకే,
madam. Nearly 50 members are participating, madam.
ఓకే, అర్థమైంది. వాళ్ళు ప్రాబ్లమ్స్ లో ఉన్నారు. ఓకే,
Yes, madam. Yes, madam.
సరేనండి.
Okay, madam. Bye, madam.
సరే, నేను లాగ్ ఆఫ్ అవుతున్నానండి అయితే.
Okay, madam. Bye, madam.
సరే
మేడం, ఫీడ్బ్యాక్ లింక్ పెట్టండి.
ఫీడ్బ్యాక్ లింక్ అంటే ఏంటండి మీ ఉద్దేశం? నాకు అర్థం కాలేదు.
మేడం, దీంట్లో ఉంది మేడం ఆల్రెడీ.
గూగుల్ ఫామ్ పెట్టారు.
గూగుల్ ఫామ్ ఉంది మేడం ఆల్రెడీ లింక్.
ఫీడ్బ్యాక్ లింక్ అంటే అటెండెన్సా?
ఎస్ మేడం, అటెండెన్స్ అండ్
సరేనండి. ఐ థింక్ ఇట్ ఇస్ ప్రొవైడెడ్ అండి. నిర్మలాదేవి గారు, మేడం, ఇట్ ఇస్ ప్రొవైడెడ్. ఐ థింక్ మేడం లాగా పోయినట్టున్నారు. సరేనండి.
ఓకే మేడం.
సరేనండి, నేను కూడా లాగా
అవ్వలేదు మేడం. ఓకే మేడం, లాగా అవ్వలేదు మేడం. ఓకే మేడం,
ఇచ్చారంటండి.
చూస్తాను మేడం.
సరేనండి.
ఓకే మేడం, థ్యాంక్ యూ.
థ్యాంక్ యూ అమ్మా.